Welcome to the video Terminal Velocity 2. In Terminal Velocity 1, we analyzed the motion of an object falling under the influence of gravity and with a linear velocity-dependent drag force minus k vector v, so opposite the velocity. And we started out from Newton's second law, and we had m times the acceleration, which was dv dt, is mg minus kv. And we did lots of algebra, and calculus, and got to the expression v equals mg over k times 1 minus e to the negative k over m times t. In this video, I'd like to explore some of the graphs that are associated with this motion and explore the acceleration. So, as we talked about in the previous video, at t equals 0, v equals 0, and at t equals infinity, when you plug infinity in here, 1 minus e to the negative infinity, e to the negative infinity is 0, so 1 minus 0 is 1, so the velocity is mg over k, which we also said was the terminal velocity. So it never actually reaches mg over k, it just gets very close. So the graph of this function, velocity is a function of time. Here's the time axis, velocity axis. There's an asymptote at the value v terminal, where v terminal is mg over k, and it starts at 0, and it increases at a decreasing rate until it reaches, or is asymptotic to, mg over k. Okay, so that's the graph of velocity as a function of time from t equals 0 to t equals infinity. Next, what I want to do is take the derivative of the velocity function to get the acceleration function. Acceleration dv dt, which is the derivative of, oops, that's a crazy looking parentheses sign. Let's try that again. Derivative of mg over k times 1 minus e to the negative k over m times t. So the derivative of, well, first of all, this is a constant. None of these things changes with time, so that just comes out in the front, mg over k, times the derivative of 1, which is 0, minus the derivative of e to the negative k over mt. Now, the derivative of e to the ax is a e to the ax. In this case, a is negative k over m. So derivative is e to the negative k over m times t times the a here, which is negative k over m, negative k over m. So that means I have mg over k times negative and negative is a positive, k over m, e to the negative k over m t. So if you look carefully, that k cancels that k, this m cancels that m, and what you're left with is g times e to the negative k over m t. And there's your function for the acceleration. And let's look at what that looks like. The acceleration at t equals 0, g times e to the negative 0, well, e to the 0 is 1, so the acceleration is g times 1, which is g. So the acceleration starts out at g, which, if you go back to the velocity, or back to Newton's second law, at t equals 0, the velocity is 0. So m dv dt equals mg, the acceleration equals g, because there is no velocity. There is no velocity or drag force either, because the velocity is 0. So at t equals 0, the acceleration is g. How does that manifest itself on the velocity graph? Well, right here, the slope of the velocity graph is g at the beginning. At t equals infinity, g times e to the negative infinity, e to the negative infinity is 0, so the acceleration is 0, which makes sense because this line is approaching the asymptote here and becoming more and more horizontal. At infinity, it is horizontal. So I'll choose a different color here to draw the acceleration graph. time axis, acceleration axis. It starts out at a finite value g and then decreases. Oh, that's not such a good asymptote, but you get the idea. It's asymptotic to 0. We'll put that here. Approaches 0. So just to recap, we started out mg, drag force proportional to velocity, wrote out Newton's second law. In the previous video, terminal velocity 1, we went through calculus and algebra to get this function here. And from this function, we drew this graph of velocity versus time. We took the derivative of that function to get the acceleration as a function of time. The acceleration starts out at g and decreases asymptotically to 0 over time. Acceleration graph is the slope of the velocity graph. And this concludes terminal velocity video number 2.